First of all, I have to clarify that now I am in an airport.
Stop. Show me your passport. Where are you from? What's your job? Why do you come to England? What do you want to do here?
Oh, sir, I am just a poor PhD student from LMC PFL. I come here for a conference about material science.
Be more specific, please.
Okay, shrinkage of cement and concrete.
Cement, concrete. And you? For a girl, I don't think this subject is very interesting.
Excuse me?
Why do you want to do a PhD research about it? This cheap and common material.
What?
You've already used it for hundreds of years. What can you do about it?
Okay, if you say so, but music. You won't let me go if I don't tell you. Let me tell you whatever I should say. I will show you in a short time. I've been thinking this song for quite long. Okay, a moment please. So, ladies and gentlemen, good afternoon. Thank you for staying here for my presentation. And now I think today is really good for me to clarify what is cement and what is my thesis project. First of all, I would like to answer the question is why do we need to care about shrinkage of cement and concrete? You may not believe, but cement is actually one of the most used materials in our daily life. And you cannot imagine how amazing it can be. Look at these pictures, and it can be any kind of shapes. It can be penetrated even, and you can make like a Christmas tree for it. And I will give you one example how like amazing it can be. Let me find a nice-looking guy here. Of course, all of you are nice-looking, but I would like to find one. Okay, so you please. Do you have a girlfriend?
That's it.
I'm so sorry, but just, okay, doesn't matter, but
Maybe.
okay. Please come to my lab tomorrow or whenever, and I promise I will give you a cement ring for you to propose. And I'm pretty sure, oh no, actually 100% sure, you will get, your girlfriend or imaginary girlfriend will say yes to you.
I sure that's a good idea. It's brittle.
Come on, yeah, it's brittle, but I will make it, I will let it won't break. And it will be unique and creative and cheap. It's a very good idea. Come to my lab next week. But nothing can be perfect. So sadly, our cement is also not perfect. So one of the biggest problems for it is it actually have some cracks, sometimes. Of course, not most of the time. But the thing is, we cannot avoid it. Why? I would like also give you another example is that, for example, yesterday you went to Lausanne to buy a nice pair of trousers, and everything is so nice except there's one crack in the middle there. And what will happen if you do a squat? Like this? Oh God, it's so embarrassing, right? Especially in front of a lot of people like today. Luckily, it was not me. But the thing is that you cannot use these trousers anymore, and if you want to repair it, you will have to spend quite a lot of money, or not a lot, but still you need to spend some money. It is exactly the same as for our cement. So if we have some cracks for our cement, then it will sharply reduce our durability and also the service lifetime. And I think no one would dare to live inside of a house which has lots of cracks there, right? So we do not want cracks. So that's why here comes the second question, is how or why we will have some cracks. So there are a lot of reasons for it, but one of the conditions it has to reach is that the tensile strength of inside of the material has to be higher than the tensile strength, then the material cannot handle this stress anymore, then it will just crack. And all the deformations, when the cement is restrained, all the deformation caused by the temperature change, the moisture loss, or external load, or the phases changing will all cause the tensile strength increase. So all these deformations are very important for us, but I will just focus on the original shrinkage, because 4 years is not enough for me to understand everything. So I decided just to focus on the original shrinkage. So my final goal for my PhD research is to predict the original shrinkage based on the mechanism or the microstructures of the systems. So first of all, we have to understand what is the mechanism for original shrinkage. Let me tell you, it's very simple. It actually comes from the capillary pressure. So the capillary pressure is caused by the formation of the water-air meniscus in partially saturated pores. So this is another graph shows you like the relationship between the relative humidity, capillary pressure, and the microstructure. I will not explain it in details, but actually the main information from this graph is that when the cement is hydrating with the water, the relative humidity inside of the system will decrease, and it will give rise to the capillary pressure. It will increase very sharply. Then this will give the deformation. And it also linked with this Kelvin radius I called here. It actually presents the microstructures inside. So now you may have another question: is what is the real microstructure in the cement phase? Because for you, maybe cement is just a very dirty kind of materials. You can see every day it's very dirty, and no one wants to touch it. But if you look at this concrete wall, if you look closer, actually it's not that easy. It's actually some like, if you look closer, look, this is the cement, unhydrated cement grades, and also you have cement hydrated products, and you also have these pores inside. And if you look these amorphous phases, it's not just amorphous. If you look closer, then it's like needles everywhere. It's like flowers. You may not expect this, right? But this gives us an idea of how
So complicated.
Yes.
How do you predict it?
Good question. So I have to tell you how I predict it. That's why I wear this kind of costume today. I made by myself. And yes, as you see, even though the microstructure is so complicated, I have to find a way. How? It's like I just use these simple spheres to present as cement grains. So just imagine I am a cement paste now. So this is cement particles. Surround me is just water. So we'll react and so no, I think it's better to first explain a little bit about this model. Is that these cement particles, and we will simulate like the the hydrogen products. So basically there are two kinds of cement hydrogen products. One is the inner and outer CSA gels, which I present as these layers, the green layers here. And another kind is polyandrite, which I didn't show it here because it's also another different kind of spheres. Sorry, I don't print it in like another color, but it's actually there. So this is the model I made by myself. It's a geometry model. It also shows you how it will hydrate, and when the hydrogen goes, how the phases will form and how the microstructure will change. And at the same time, this system, this cement paste will sometimes shrink or expand, or shrink or expand. It really depends on what kind of condition it is. Of course, not this big scale, because otherwise we can just see it. We don't need to use very high technique to test it, right? And also, this cement grades will change. It will like grow, or it will like be consumed. And now we have already get these microstructures. But if you want to get the original shrinkage, still we need another help from this equation, thanks to these two scientists. They're very smart, and they help us to link this microstructure, the relative humidity, and original shrinkage together. So if we are able to test all these parameters, we will be able to predict the original shrinkage. How? We have techniques to help us. Look at this technique here. It is called a water activity sensor. It will help us test the relative humidity inside of the system. So this is a very key parameter for us to predict the capillary pressure. And these two techniques, one is the MIP, another one is NMR. Combine two of them, we can have an idea about the pore size distribution inside of the systems as a function of time. Like during the time, you can also see how it changed. And also, you can get the information about the water populations inside. And by combining all these informations, we can get the predicted original shrinkage. And we will combine this predicted original shrinkage with this experimental data, which we did with the corrugated tubes. Then we will see if our prediction is good or not. So here I show you one of my predicted results. Every time I saw this, I feel so sad because the result is not really very good, because you see, the green line is the predicted result and the black line is the experimental result. They are not well matched. So sad. And one of the explanation is cement is not pure elastic or plastic material. It is actually kind of a viscoelastic. That means when it's loading constant, it will still change the shape. So it tells, sorry, I was a little bit late, but that tells me that I still have a lot of difficulties and challenges to meet, and I still have 2 years, by the way. And I have to try to simulate this mismatch, and I have to try to apply this model to more complicated systems. And at the end, I still think the biggest challenge comes from myself. So I asked myself to be stronger, and stronger, and stronger. So...
Enough.
Okay,
Stop.
so...
Too talkative. You can pass now. Please, go.
Okay.
Catch up.
Thank you very much, and thank you for all